Couchsurfer has a problem. He loves music, and he loves jazz music. And he loves it so much, and he got into the bass, into the bass thingy by the music. So he thought about, well, what can I do? I like the music. Maybe I'd love to play an instrument, and I love to learn, and I want to play with wood and machines and metal, and want to tinker and want to invent and engineer. So he put it all together, mixed it a bit around, and the result was he made a bass guitar himself. Very impressive. As far as I know, the only things he bought were the strings and some threaded rods. Please welcome Couchsurfer, the guitar man.
Thanks. So before I start, I'd like to know who of you plays a guitar? Oh, that's cool. Who of you actually built one? Oh, I see a hand that's up. That's awesome. I want to talk to you later. So, a little bit about my background. I'm studying civil engineering. I lived in Aachen and traveled to Cologne to the Dingfabrik, where I built my first guitar. And about a year ago, I moved to Karlsruhe and now basically live at the Fab Lab. And that's where I built my current guitar. And yeah, I have a slight background in photography, microcontroller, and Arduino programming. My first computer was a C64. No, not actually my first computer, but the first one I really understood the bare bones of it. And I'm really into computational theory and language security. And if you want to contact me, the context, I prefer Java or Irk. Yeah. Einbal has a problem. He wants a nice guitar, and he wants an awesome guitar. He wants a custom design that's never been done before. He wants to control the entire manufacturing process. He wants to do it all by himself, from scratch. And he wants to learn a lot about building guitars. So, first of all, he needs tools. And the first tool is a bandsaw. You could use a table saw, but with hardwoods that are usually used in guitar construction, table saws have their limits, and bandsaws are much easier to use, and you can extend them much further, mill bigger pieces. And the other thing is you need a plane. And there are these really big, awesome airplane carrier planes that are really expensive and cool, and you don't actually need them. You can do it by hand. I bought my raw lumber pre-planed from a guy I know, and so I don't actually have to use one of those big planes, and I can use a fancy hand plane. And you actually get into sharpening planes, and it's a nice hobby. The next thing you need is a rasp to do the contours. I tried doing them with a table router, but I found that those are really clean and continuous, and you actually want some flowing forms, and doing it by hand with a rasp gives a much better result. And this is a Shinto rasp, a Japanese saw rasp. Those are actually saw blades woven together to form a rasp, and these tools are really awesome. I bought it for working with bubinga wood, which is really hard. It has actually more properties of metal than wood, and this thing just bites through it like butter. It's really cool. Then you need a lot of clamps, really a lot of clamps. You can never have enough of them, because this is gluing on a fretboard, and you could use wood to dispense the pressure, to spread the pressure of the clamps, but you only get so far with it. You really need a lot of clamps. And of course, a table router. This is just a little motor that has these cutter bits in it. It sticks through a table, and on the top of it are ball bearings, so you can manufacture templates and put the template on the piece of wood and make the tool head follow the template. More on that later. A CNC is really great. it's not mandatory, but I found that especially like milling out pickup cavities is much easier using a CNC machine. And they're fun to work with, so why not? Another thing is 3D printers. Also not mandatory, but really useful. And I use the lathe because we have a lathe at our Fab Lab. And yeah, you need to, if you want to do hardware yourself, you really need a lathe to do the knobs. Wood. Yeah, this is pretty wood. This is like birch and walnut and spotted maple. And this is what we usually use in guitar building. It's really pretty, it's really expensive, really rare, but it looks just awesome. And those woods look good, but they can't really support weight because the fiber in this wood is running crazy. And yeah, this is nice for a top to look good. The actual requirements for the wood are moisture content, because when the moisture content changes in the wood begins to move. And you don't want that, because that produces cracks. So a figure that you can work with is about 5% of moisture left in the wood. And you could say about 1 year per 2 centimeters of thickness of wood to dry to 5%. And yeah, that measures out for planks you use for guitar building to about 3 or 5 years that this wood needs to be stored. And you can actually accelerate it with ovens, but that usually tends to create tensions in the wood that release when sawing it or milling it, and yeah, it's not really that awesome. No faults. You don't want knot holes, insects, something like that. But these woods actually have some faults, but those faults look awesome. Like the spotted maple is a maple tree that grows in a swamp with special minerals in it, in the soil, and then the bacteria gets into the wood and actually pushes these minerals into the cracks, and that actually forms those nice stripes. So sometimes you're looking for defaults. And I also saw some guys actually building a tele guitar with pine wood with as many knot holes as they could find, just because they like the look. So yeah. Yeah, we use hardwoods, and hardwood is a bit of an overloaded expression. I think it originated in toll booth, because hardwood was just, you had to pay a different tax on hardwood than on regular wood. And after that, it all got mixed up. Basically, what it means is that it's denser. It's really dense wood. It has high strength, long grain, long fibers, and dense annual rings. And it's not dependent on the species. You can actually grow a species that's a softwood in bad environment, and then it grows slower, and you can make it have the same properties as a regular hardwood. Yeah, and then I put some measurements in there. That's just what you usually need for guitar building, and yeah, combining these facts, you end up with you have to pay a lot of money for good wood, but it pays off. It can become an awesome instrument. There's another thing, that's milling, because trees don't grow like boards. There are these strange round things, you may have seen them if you go outside, and we need to make boards from them. And to get these boards, there are a few ways to mill them, and usually what's the most effective way is the one in the middle, the quarter saw, because these rings in the wood, they almost are perpendicular. And you can imagine that if you have these fibers stacked, that you can actually compress them really easily, but it's really hard to pull them in the direction of the fibers themselves. So if the moisture content changes, if anything in the environment changes, the wood tends to move in the direction of least resistance. And with quarter sawn wood, you have almost perpendicular rings, and that means that it's only moving in one direction. And you can work with that. You can work around that. That's predictable. If it's not, it moves in strange directions wherever the grain is running, and it can be quite hard to work with and create cracks, what you definitely do not want. But lengthwise sawn wood has this really, really nice texture, and that's what you usually use for fingerboards, because those are glued on the neck, and the neck is already very, very strong, so it won't move if the fingerboard starts to release some tension. Okay, let's get actually started and build a guitar. So I'm going to run through some theory and then talk a bit about what I did and about applying that theory. And I brought some guitars with me, and I might hold them up and show some things. Yeah, we will see about that. First of all, the hardware, the thing that actually holds the strings and create and gives you the ability to tune the string by applying tension to it. It also should not only tune the string, it should also you want string spacing. You want the same space between every string, and I found that a little bit of movement, making them a little bit narrow, actually changes the feeling of playing the guitar quite a lot. And so you want that to be a variable, something that you can adjust. It's also the action. The action is the distance of the string to the fingerboard or to the frets. And that's a taste thing. Some people like to play with really high action. Some people like to play with low action. But that's also something you really want to adjust, especially because the head is the neck is moving. Yeah, the hardware should fix the strings in place so they can vibrate. And usually that's done in 3 parts. You have a bridge, that's the tuning system, the part that controls the action and the string spacing. You have a nut that holds the strings in place up here on the head. And whoa. Sorry. I don't know what happened there. So the nut holds the strings in place, and the tuners actually pull on the strings. In a headless guitar, these things move kind of together and accumulate in 2 points. The headpiece and the nut are for fixing the strings and are basically one unit, and the bridge and the tuner are on the bottom. And I will go into that later, why that's a really awesome design. Yeah, designing a headless tuning system. It turns out, if you don't want to wrap your string around some rods, but actually want to pull on the string directly, you need about 20 to 30 millimeters of movement to tune a guitar string. Yeah, a guitar string. A bass is also 20 to 30 millimeters. And I think that's version 7 of my design. I made the first design, and it wasn't possible to manufacture this at all. You would need special tools that are much expensive. And so I went through a lot of iterations and finally came up with this design that's easy to manufacture and works really well. And it basically just holds the string, and then you can pull a knob, and that knob pulls in a little threaded rod that's fixed at the point where the string is grabbed, and so the string gets moved along and tension is applied to the string. Yeah, I milled that part on the CNC at our Fab Lab and actually wrote the whole code for it in G-code parametrically. So if I want to change anything about the design, I can just change a variable. I don't have to go through post or pre-processing anything. I can just change a variable, load the code up in the CNC, and do it again. And this is only possible because I chose quite easy and straight geometry. And yeah, simple is most. Sometimes you need a lot of time to get to the most simple solution, but it turns out to be a really good one. The knobs are done on the lathe, and this is completely hand operated. These knobs aren't knurled, and I found out that you actually need some structure on the surface to really grab them. And so I added some knurling to them, and after that I found out that actually the diameter isn't enough to apply enough force, so you don't have, so you can tune the strings. And so I made new tuner knobs with a wider radius, and now they're working just great. Really, really awesome tuning system. I can only recommend getting into headless. Yeah, and the headpiece. The headpiece is also milled at Fab Lab, and yeah, there are just set screws in there that fix the strings, and it's a quite easy piece, but took me about 8 iterations to get it right because there were always something wrong, and oh man. But it's all also written in parameterized G-code. And yeah, so if I ever want to build a 7-string bass, I just change one variable and it will just mill it. And that's how the tuning system looks in the end. So you can see that the part where the string is grabbed and the threaded rod that's pulled into the knob, and the saddles where the strings are sitting, and you can adjust the action. You can't adjust the string spacing in this design. I haven't really figured out how to do this properly because all the designs I've figured out so far have some flaws in them. And so I decided to do this statically. If you have some idea how to fix this, please talk to me. Yeah, let's get into the user interface, the neck. Most necks are laminates. And that's because, I told you about wood moves, and wood moves in the direction or perpendicular to the direction of the fibers, the grain structure. And so what you usually do is you just saw one board in half, turn it around, and glue it together. And this way, one side of the board wants to move in the left direction, one wants to move in the right direction, or up and down, and those movements cancel each other out. And that's the whole idea behind 2-piece laminate necks. And they look quite nice. It's a nice optic. And if you want to really have a strong neck, you can always do like veneer lamination and make the pieces of wood you join together like 0.6 millimeter thick, and yeah, then you basically eliminate all the effects of grain structure in the wood. Necks also have a truss rod. And a truss rod is just a little piece of metal, actually 2 rods in the neck. And those rods are, so one is threaded and one is static. And if you pull on it, it tries to bend. And this way you can actually adjust how much the neck is bent. The neck will always bend. It will bend due to moisture change, due to weather change, temperature. Travel guitars have a special way of construction because there you have a lot of change in weather, and the effects are huge, and you have to tune them all the time. And it's also a thing because you don't want string buzzing. If you want a slight bow in the neck, actually, you don't want a straight neck, because if you pluck a string, it's moving much more in the middle than on the ends. And so you want a slight bow in the neck, so you can account for that and actually get a lower action than it would be possible with a straight neck. And that's why there are truss rods in guitar necks. The vintage truss rods were actually 1 rod, and the problem with that is you need to pre-bend them, and you actually need to mill a concave structure into the neck. That's not easily done, and you can only adjust those in one direction. So modern necks usually use this design, which is also called dual action truss rods. If you are paranoid, or if you're building a travel guitar, or if you're building like, I don't know, a 10-string bass, you might want to consider carbon rods. Those are just stiffening rods that support the neck. And yeah, that's what I said before. Like, if you have a travel guitar and the moisture content is changing rapidly and extremely, and you just want a little bit of support on the neck to fix it. One really important part is where the headstock meets the neck. And the most obvious and easiest way probably to do this transition is to just make it flat. And that's actually a nice way of constructing. I think Stratocasters usually have necks like that, because you have two planes that you can reference during construction. The problem with that is that, first of all, it's a nice construction because you get a lot of forces running in the direction of the fibers, of the grain, and that's where the wood is strong. The problem is the break angle. You have a different angle on each string, and you don't really want that because each string will transfer different amounts of vibration from the part that you are picking up to the part that's going to the tuner, and you get tuning instabilities. And the easy fix for that are string trees. You just pull the strings down. It's a design. A much more elegant design would be to make an angled headstock, so you automatically get the same angle on each string. You might already see the problem with this. You get a lot of forces perpendicular to the grain structure, and this creates a weak point. It's not so weak that it breaks due to string tension, but if the guitar is stringed up and you push it a little, it might do the trick. And actually, that's a huge problem with old Gibson guitars. You can find them on eBay and looking like this, and that's exactly the point where they're breaking, where the shear forces in the wood couldn't be supported anymore because of the grain structure. The easy way to fix that is to just leave it, saw out a different part of the same wood you're using for the neck and glue it back on, so you get the grain structure running in the direction of the headstock, and you get the only shear forces you get are in the glue joint, and glue joints are usually much stronger than the wood itself. The thing with this design is that you get a visible connection. You can hide it quite good, or you can actually highlight it to make it look nice. Like in the one picture, there's a veneer added to it. And yeah, this is a really strong design, and I did this on this bass that I built at the Dingfabrik. And I used two woods, so this is mahogany and this is walnut, and you can see the transition. And this is a really, really strong joint. It's actually not that hard to manufacture, because you can just saw off one piece at an angle, put them together and go over this angle with your plane, and you will get two surfaces that are joining quite perfectly. The thing is that the fingerboard is running over the piece of wood that's on the headstock, and so you need to build it in a way that you have a perfect plane all the way through. And yeah, the easiest way to get it is to just put the pieces on top of each other and use a plane. A different way I saw to do it is incorporating a dovetail joint into this, and this is really, really awesome woodworking. And I think, yeah, this headstock will never break off. It's crazy, but it looks really awesome. Another way to get around this weak point is to add a volute, to just leave wood at that point where you get the weak spot. And that's often done in classical guitars, in acoustic guitars. And you can really work around this. Like the picture on the bottom actually has an asymmetrical volute with veneer pieces glued in. And I just love this design. This is just awesome. I mean, where have you seen something like this before? The most easy fix for this is to just omit the whole problem. Just go around it all completely and do a headless design. And then you don't need a headstock. You just need this piece of metal that's fixing the strings. And yeah, that's what I did in my second design. And it's a much cleaner solution, I think. Yeah. Yeah, the front part, the fingerboard. The fingerboard is the actual user interface. I mean, this wasn't right what I said. It was more or less the backbone, and this is the user interface because that's where what you're touching with your fingers. And this is really delicate. You're working with your hands on this stuff, and you have to be accurate to about 1/10 of a millimeter. So you have to work this stuff really procedurally, and yeah, you have to be really accurate. Usually fretboards have a radius in them. And that's just, yeah, it's basically just preference. I built my first bass with a perfectly flat fingerboard, and it was totally weird to play. It was, I don't know, it just felt wrong. And some people actually prefer really small radii, and some prefer really big radii. I prefer big ones. I think I always use 14 or 12-inch radius. And to get this radius consistent, you just use a sanding block and move it along the fingerboard and make sure that you're visiting each spot the same amount of time. So you can be sure to get rid of the same amount of material on each spot. And this is the easiest way to get a radius, but the problem is you have a constant radius. And if you think about how a string is strung up on a guitar and how the fingerboard is running, the strings are much closer together on the head and a bit farther apart on the bridge. And so what you actually get is a compound radius. And that's much harder to achieve. There are installations like this, like you have two pendulums, and a sanding machine on the bottom. And this way you can get a compound radius quite easily and quite consistently. People have built jigs to achieve this. And you can also do it completely by hand. But this takes mad skills and a lot of practice. And if you've actually tried to plane some ebony hardwood, I did, it's a pain in the ass. You need a lot of elbow grease, and you're not getting very far. And oh, man, it's so hard to work with those woods because you need strong, dense wood for your fingerboard to hold up to the mechanical attack from the strings and from the sweat from your fingers, which is also really aggressive. And yeah, you need strong wood on this part. And strong wood is hard to work with. And I found that actually with large radii, you don't need a compound radius because the difference would be so small. I think only 0.2 of a millimeter is what I came up with. And yeah, it's a game of tenths of millimeters, but it's a game of tenths of millimeters on the length. So you just need to be consistent. And yeah, I can't really, I have to try that. I never did a compound radius, but so far it works out. But if you're doing small radii, you should really consider compound radii. Okay, scales. Now we have the cross-section covered. Now we need to cover the length. The basic theory of scales is just you have a string that's fixed on one point, fixed on the other point, you plug it, and it vibrates on the frequency. And if you halve the string, so if you pull it down in the middle, you halve the wavelengths, and you get the same frequency just an octave above. So the same note, just an octave above, half of the frequency. And if you have the part that's left again, you get another octave and so on and so on. I only put 2 octaves on here because that's about what most guitars use. If you have the octaves, you can divide them even further. And usually we do that by 12 semitones, at least in Western music. And this isn't accurate. Actually, it is because they're in brackets equal temperament, because this is equal temperament. Depending on the key you're in, notes fall in different places. And this design, where you have these straight lines, this is just a compromise, basically. A compromise so you can play in every key and still hit about the right note, but not quite. And there are solutions for this. People have worked around it, and they look crazy like the one on the top. I think these also have some microtones in it and some really weird and awesome Arabic music. And the one on the bottom is a dulcimer. And the dulcimer only has frets at the notes of in one key. It's perfect intonation, but you can only play it in one key. Well, I want both. I don't want to compromise. And with a bass guitar, you can actually do this by doing a fretless. So what I'm doing is just where the notes would fall on an equal temperament, I put some veneer strips in the fingerboard, so I have a marker where those notes would fall. But while you're playing, you can listen to the sound and you more or less play by feeling. And then you can play equal temperament, but you can also play just intonation and other really weird intonations and scales. There's another problem. And yeah, the frequency of a string is governed by the mass of the string, which is quite obvious, the scale length, and the tension. And you try to work around this by using different string gauges. So the strings actually have different mass, but you only get so far with it. For a regular bass guitar with 6 strings, I got the distribution of tension, and yeah, it works out. I mean, 75 newtons to about, 145 newtons, no, 270 newtons. You can work with that. That's not a problem. But if you want to build extended range instruments like 8-string guitars or 7-string basses, you get a problem that the tension is falling down to get to lower frequencies, and you can't actually play them anymore because the strings get floppy, or the higher strings have too much tension and it's not fun or doesn't feel good to play. So let's change some variables. We can't actually, we can change the mass of the string, and we already do that, but that's just a small factor. You can't go get very far with that. You can change the tension, but the tension, no, you could change the frequency. The tension is the problem we want to solve. You could change the frequency, but you don't want to detune your guitar. I mean, you still want to be able to actually play it. So what you do is you change the scale length, and you change it for each string. So you get a multi-scale guitar. And this has the effect that the frets actually have this fan shape, and that's why they're called fan frets. So it's easy to get. You just use the highest and the lowest string, calculate the points where the frets would fall on this string and on the top one, and then you just join them with a line, and you get this shape. And I'm now building a 6-string bass, and I really want to be able to play it and feel nice when you're playing it. And so I decided to go for multi-scale. Now, the weird stuff is this is fretless. And I'm not really sure by now if you can actually play a multi-scale fretless, because this looks really weird. And this looks like it would be really weird to play. But it turns out that if you have frets there, you can learn it in about 5 minutes if you can already play it. It's really intuitive, and it doesn't feel strange at all. But with a fretless, I don't know. I never tried it. I never found one. So I'm doing one. The back of the neck is also something, because you're something really important, because you're basically applying pressure with your hand, with your thumb, and then with the fingers on the string. So you want to have a nice, comfy place for your thumb to rest. And yeah, there are many neck profiles. There are many like it, but this one is mine because this is up to preference. I mean, just go out there, try some, and find out what feels great for you. I can't really say much about it. It's just a shape, and yeah, there are really big ones and bulgy ones. I've seen ones that have sharp corners that are trapezoids, and they are supposed to be really great for chord work. But I don't know. I found that I like vintage D shapes, so really bulgy ones. And on this one, I'm trying a new, really weird thing that's supposed to work really cool in theory, because this on a 6-string, the neck gets really wide on the bottom, and so I'm doing a trapezoidal shape that gets wider. So the base of the trapezoid extends, the sides stay at the same angle, and then I'm rounding it over. So the further you get down the neck, the more flat space you have to rest your thumb, because you actually, on the bottom, you need more room to play, you need more space to move. So I'm quite curious how that will work out. Yeah, that's the shape in the making. So you can see in the pictures there, I started out with a trapezoid and then just rounded it over. Again, with the Shinto rasp. If you want to get into woodworking, really check out Japanese woodworking. They have amazing tools. Basically, a whole different approach to woodworking. Really interesting. Okay, at some point, we need to join the neck to the body. And there are basically two extremes. The first one is bolt-on. You just mill out a pocket, put the neck in, and screw it down. The other extreme is you actually don't really build a body. You just use one piece of wood and put wings on it. And that's what I usually do. So you can see this whole neck goes through all the way, and then there are just 2 wings of wood on the side, and this makes up the body. And these 2 designs have 2 very different characteristics. The through neck design really enforces the lower frequencies. And the bolt-on really enforces, and it dampens the lower frequencies and enforces presence, the higher frequencies. And that's actually because the vibrational character of the different woods, and it's actually, you have 2 different materials joining at one point, and you're transmitting vibration through them. And yeah, if you have this joint, it's never going to be perfect, and it's going to be different woods, and you lose some frequencies, and lower frequencies are harder to transmit. And you can actually scale this. So there are guitars that have set-in necks that are glued in and go like maybe halfway down the body. And so you can have a parameter you can play with here. You can basically add lower frequencies by making the joint extend further down into the body. I will later talk about why I only build through neck. First of all, I think it's just a cleaner design, and but that's another reason. We will get into this when I talk about pickup and pickup designs. The body itself. The easiest and most obvious way probably is to do a solid body, so just one piece of wood. You mill in the pockets for the electronics, for the pickups, and for the neck, and you join everything together. The problem is you have a solid piece of wood, and as I said, we usually use hardwoods, and hardwoods are dense, and so the guitar will be heavy. And to avoid that, you can build a chambered instrument. At this point, you might want to use a top. This particular one, just the guy just glued on veneer on the back of the guitar. But the usual way to construct this is to build the body, put in chambers, and then put on the top of like some really nice burls or spotted maple. Just wood that has a nice figure. And there's also the reason why this guy didn't just make one huge chamber and made those little holes. First of all, I think he just loves Forstner bits, and I agree, Forstner bits are awesome. But there's a reason, another reason, and that's if you make one big chamber, you're moving closer and closer to acoustic guitar construction. And in an acoustic guitar, the chamber vibrates, the wood vibrates, you get standing waves. In an acoustic guitar, you want that. That's actually what makes an acoustic guitar sound, because the strings themselves don't move a lot of air. The wood is moving the air in an acoustic guitar. And the problem is if you have this kind of shape and you make a chamber in it, you can't really control the standing waves. The problem is you get wolf notes. So at some points, at some particular frequencies, you get really high resonance or sustain, and at some points you don't. And so you have an uneven response over the neck, and yeah, you don't want that. And that's why he used these little chambers. Yeah, acoustic guitar, this one is hollow body construction, and you already see remnants of an acoustic guitar. I mean, if the huge block of wood in the middle wouldn't be there, it would be an acoustic guitar. And yeah, this is also a way to construct, but at this point you have to consider like the thickness of the wood you're using, because at some points, at some thicknesses, different woods vibrate differently and get different sustain, different sounds, and yeah, that's much harder to do. This is the design I started out with. This is this one. This was the first one, and I just drew it up in Inkscape and moved around the Bezier curves until I liked them. And I don't know, it took me some weeks. I just opened up the file, looked at it, thought, man, this doesn't look right. I moved it around, changed something. And then for the second guitar, I took the same design and changed it around. And so it's an evolving progress. And if you don't want to rebuild a guitar where you have the plans readily available on the internet, you should maybe draw it up on paper or draw it in Inkscape or some other program and move the curves around until they look right. And then you get into the problem that you now have a digital design, but you want a physical object. And so how do you transfer this design onto the wood? Well, you could print it out, sand down the wood until it fits the curve. Boring. Lasers. We have a laser cutter at our Fab Lab, and there will be a talk tomorrow about it by actually my herald, Sarah, who introduced me. And yeah, that's what I used. Just put the Inkscape design into the laser cutter. It already understands it, converts it to G-code, and cuts out the templates that you can later use with a table router to transfer these designs onto the wood. The easy way. Yeah, first of all, I joined the Bubinga wings with the walnut burlwood, cut them out roughly, and then I tried the thing with the router and found out that I have woodworking tools and I want to work with Bubinga, and Bubinga has actually more characteristics of metal, and it didn't work. It just threw the workpiece all around the shop, and it was quite scary to work with that. So I used a belt sander and a drum sander, and that worked out quite great. But usually you want to use template routing bits with these little ball bearings on top, because you can be sure that you have the design you drew up digitally and transferred to a physical object. Then you glue on the wings. And this guitar, it's this one. I put some veneer stripes of Wengi between the wings and the neck, just to accentuate the difference in wood, in color and wood structure. Yeah. Well, electronics. All guitars look like that inside. No. This is a Moog synth guitar. I think it's from the 80s. They did something really, really great with optical pickups, and this is a whole synthesizer board. Most guitars are much simpler, and there are two ways to do electronics in a guitar. The first one is active, and that basically means that you have a little operational amplifier on a small PCB that decouples the whole circuit from the cable that goes to the amp. So you have a low impedance output, and it gives you a different sound, but it also eliminates the cable from the components that actually make the sound. And you also have some possibilities with that, because you can actually build a nice EQ with boosts. So you can actually boost frequencies instead of only cutting them. The downside is you need a battery. Another way to do it is the old school way, passive. And yeah, it's just a simple circuit of a potentiometer and a capacitor. And yeah, the output is high impedance, so the cable becomes part of the whole signal chain, and you can get some weird effects and humming, and you should shield these things. But I always did passive electronics, and they worked out great for me. I liked the sound. And another great thing is, I like the sound of passive, and I want to get into active, but I want to incorporate a whole DSP, and I'm talking to Einball about that, and maybe at another Chaos event I will talk about incorporating a DSP into a guitar. There's the electronics. They were boring, let's be honest. The most interesting stuff are the coils, the actual pickups. And you see there's this coil, so there's just copper wire wrapped around the magnet. And yeah, you see 6 magnets here, but those actually act like one huge magnet. And so a pickup can't distinguish between the individual strings. That's also why the Moog guitar uses optical pickups, because with that you can actually distinguish between the different strings, and you don't have to go into weird Fourier transformations and analysis of overtones and stuff like that. Yeah, pickups. There are also piezo pickups, and those are quite fun to play around with, especially because you can attach them on any point on your guitar and see what sounds you get. And there was some guy on a forum, I forgot who it was, he attached the piezo on the neck, and he found that actually on a bass guitar, there's on the 1/3 of the scalings, there's a sweet spot for a bass guitar. And at this point, you wouldn't be able to get a pickup, to install a pickup, but you can install a piezo and get a really, really great full sound. And they're easy. You don't even need a preamplifier. You can basically just connect them to your amp. If you want to pair them together with traditional coils, you will need a preamp because they are quite low output. Yeah, and then there are optical pickups, but I won't get into those. Let's stay focused on magnetic, because there are three types. There are active, and those active pickups are basically just they don't want to. It's quite complicated to do the turns, because on my pickups I use 10,000 windings of copper wire, and you can get away with much fewer if you just incorporate a little amplifier in the pickup itself. And that's what active pickups are. They just use fewer windings and put a little amplifier in there. And they usually get a more mid-range accentuated tone. But some manufacturers actually include a little tone shaping circuit that makes them sound like a traditional pickup. Another way is the usual single coil and the humbucker. The humbucker are just two single coils joined together, but with reversed polarity and reversed winding direction, so you actually get a hum canceling effect. Okay, those are the two pickups I built for both guitars, and usually I think they are done with like paper mache coated with some resin. I just printed them out on a 3D printer in our lab, and a good friend from the lab printed this case for me with really awesome quality on his own printer that he designed. Because these things are just designed to hold the windings of the coil and the magnets. Yeah, the windings. This is 44 gauge American gauge wire. This is 1/4 of a millimeter in thickness, including the insulation. A 20th of a millimeter, I'm sorry, 0.05 millimeters of wire. These things rip apart really easy. I tried to wind them by hand, and you just have to breathe on them and they break. The way to get it done is get a machine to do it. I haven't figured out to do it yet. It's not that easy, but there's a really easy solution. You don't have to think complicated here. I just used some plastic-coated paper, put the inner part of the coil on there, and moved the coil of wire around it, so that at every time I put too much pressure on the wire, the inner part of the coil just moved with me. And yeah, that was really easy. I just spent, I think, 3 days winding 2 coils and watched a lot of Lost at that point. So it takes a lot of time, and sometimes you fail. And then you have to get the copper off, and then it looks like a clown wig, and that's what the guys on the forums call it. You make a lot of clown wigs, and then you make a pickup. That's a really frustrating picture for me, because that's 1.5 days of work you're looking at. That's absolutely wasted. I wound the whole thing up, measured for continuity, and something went wrong. Yeah, and then you have to solder this small wire onto a bigger wire that you can actually work with. And if you have enough wire left, it's quite easy. You just wrap it around a few times and it works. We had a guy at our fab lab who installed a coil in his guitar, and he only had about 5 millimeters of wire sticking out of the coil. It took me about half an hour, I think, or almost an hour to get this tiny piece of wire to solder to a bigger one. And after that, you dump them. You dump them in wax. Because, think about it. You want to build a pickup, and a pickup just induces a magnetic current into the string, and the string moves, and so you get a moving field that's moving through the coils, and that induces a current, and you pick that current up and you amplify it, and you get an electric guitar. But when you wind the windings around the coil, you actually the wires are not really fixed, they move. And what have you done when you make a membrane that's moving in a magnetic? You build a microphone. And yeah, you can build it like that, and you can build guitars that are made to feedback. And those guitars you can actually scream at, and the amp screams back. And to avoid that, usually use just beeswax and paraffin, which is, beeswax is nice to work with. It has a nice, it's nice to work with, but at really low temperatures it starts to melt. And paraffin is really brittle, but it stays solid to high temperatures. So you just mix both together, and dump the pickups in there until no more bubbles come out, and you fill up all the air gaps between the windings. So those are stabilized, and you get no more microphonic effects. And then I had a good friend at the Forschungszentrum Jülich who wanted to test these coils because he never saw coils with 10,000 windings on them. And he measured them for me, and it turns out the resonant frequency is, I think, 6 or 8 kilohertz, and they are almost identical, those two pickups. These are the measurements for this guitar. So you can actually get quite similar coils by doing them by hand. The finish. The last 10% of work, but the first thing a guy sees when he picks up your guitar. Usually it's a lot of work. You need a spray booth, you apply grain filler, you apply multiple coats of lacquer, and then you sand it down. It's tedious. What I like to do is mix my own. And I just use linseed oil, beeswax. It's called, I forgot the name. It's a special wax they usually use in car finishes and car lacquers. It's basically carnauba wax. It's the hardest naturally occurring wax known to man. It's really strong, and then you use a thinner with that. I think I used something that's actually made from the same palm tree, just distilled fluid from the tree. You mix it together, scare the shit out of your roommate, because this stuff is really flammable and the smell penetrates everything. I think it actually smells quite nice, but some people may have a different opinion on that. And then I applied after the first round of sanding with like 40 grit sandpaper, and you don't need grain filler because you're filling the wood with its own dust. And then you continue, and I go up to about 1,000 grit. At 400 grit, I start to use wet sandpaper, and at this point you can actually use water because the wood is so filled with this finish that it no longer sucks up the water. And after 20 to 30 coats, it can look like this. And you can actually achieve a finish that's comparable to a lacquer finish that's much more tedious to apply. Yeah, these are the specs for my current project. So I used Bubinga, walnut, mahogany, and wangi. I'm building a fretless multiscale, which is this weird project, this weird experiment. It's headless and has an asymmetrical neck contour. The pickups are a bit strange, and that's why I only build neck-through guitars, because I use neodymium magnets that are really strong. And usually these things kill your sustain. And with neck-through construction, you get a lot of sustain, and so I can use that sustain to get higher output. And with stronger magnets, you also get more high frequencies. With more windings, you get more low frequency, and so I get a really nice balance, and I actually can get guitar sounds out of a bass guitar with this. Really unique sound, and if you roll off the high frequencies, you get a traditional, almost up bass sound. It's quite versatile. yeah, thanks for listening, and build more guitars.
Yeah, couch sofa. Thank you for your talk. I'm not going to build a guitar. I listen if you play your guitars. Thank you for being here, for your attention. Please take all your belongings with you. Don't forget anything, any relatives, any friends, and have a nice day. Bye.